Hello guys, welcome back to IIM BMSAT series. So here we are going to discuss about remainder theorems. So to find a remainder when this number 25 power 102 is divided by 17, it's not a normal division. You came to know already this thing. So how to find remainder in these cases, in this critical concepts. So here we do have multiple theorems to prove this or to solve this question. So how to do this? First thing, whenever you go for any division or any theorem, first of all understand the basic concept. What is that? 25 power 102 has to be divided by 17, right? So if I have to multiply 25 and 34, okay, let us say this is the number and I have to divide it by 17. Is it not divisible by 17? Observe carefully this number. Yes, it can be exactly divisible by 17. Why? Because it is 17 to 34. I am not asking what is the quotient or what is that number after division. I am just asking whether it is divided by 17 or not. If it is divided, there is no need of remainder. If it is not divided, what is the remainder? Clearly see this one. 17 to is 34 and the whole number is divided by 17. So there is no problem. The answer is 0. Okay, the remainder is 0. Okay, why? Because the number 34 is a factor of 17. So obviously it will divide by 17 and remainder the whole thing will be 0. So here what I wanted to say is, if you multiply any two numbers and if you have to divide with another number, you can check the remainder of these two things and these two things, and you can directly multiply this remainder 1 and remainder 2. What is the remainder of 25 when it is divided by 17? Yes, it is 8. Okay, and what is the remainder of 18 when it is divided by 17? It is 1. So the whole number, the whole remainder for this all when it is divided by 17 is nothing but 1 into 8, 8. Okay, that's why here also, even though the remainder of 25 is 8 when divided by 17, the remainder of 34 when divided by 17 is 0. So 8 into 0 is 0. Okay, I hope you understood this method, but I have to apply that for this one. So I hope you already understood this thing, that if there are these many 25s up till 102, okay, 25, it is a 102nd 25, and this thing has to be divided by 17. What is that shortcut that we can apply here? That 25, this 25 leaves a remainder 8, and it is same with this 25 and this 25, and it is same for 102 25s. That means there are 8 power 102 25s as a remainder, or 2 power 306. And if I get the remainder, if I get the remainder of this whole thing when divided by 7, it is nothing but the remainder of 25 power 1 by 102 powers divided by 17. Okay, the remainder is same as that. So again, here the problem comes again as 2 power 306, again a different number, again a bigger number divided by 17. So here I have to apply a theorem called as binomial expansion theorem. In this theorem, we will see a number, we will express a number as an addition of two terms, and we will expand that number into a normal series. Let's see. For example, 25 power 102. Before going to expand this, let's find the expansion of a plus b whole power 2. Okay, you already know what is the expansion of a plus b whole square is a square plus b square plus 2ab. But in binomial theorem, we will say that it has 2c naught into a square into b power 0. Next term would be 2c1 into a power 1 into b power 1. Next term would be, or the last term is 2c2 into a power 0 into b power 2. Okay, so here if I have to express in a generalized form, a plus b whole power n can be taken as nc naught into a power n into b power n minus 1 or n minus a. Okay, sorry, b power a. Sorry, this one is n minus 0 and b power is b 0. Okay, next term would be nc1, so a power n minus 1 into b power 1 and so on up till ncn into a power n minus 1, that is 0, into b power n. Okay, so like this we will expand the whole thing. But wait, why we have to expand here, and how can we expand this 25 power 1 by 2? What is the need here? The need is, clearly observe this, in every term of these things we have a and b, a and b, a and b, right? See here, if you don't understand this bigger expansion, see this smaller expansion. We have a and b in every term. Is it so? You may feel that, you may ask, sir, if I have taken this value, it will be nothing but a square plus ab or 2ab plus b square, right? If I have equated this value, simplified that value as this one will be a square plus 2ab plus b square. But sir, you are saying that I have a and b terms in all the expressions. Observe it carefully. I have b here also and a here also. Not only here, I have in these things also. How? But they present as b power 0, that means the value 1, and here a power 0, the value 1. So the a and b terms are expressed or can be expressed in any terms or can be seen in any terms. Okay, the only thing is we cannot get the extremes values. That's it. Leaving the extremes, in every term, in every middle term, I'll get a and b as a components or factors. That means if I take 25, as a sum of 17 and another number, okay, what is that? 8 only. If I take 25 as sum of 17 and 18, and I expand 17 plus 8 power 102 as a normal binomial expansion, will I get every term as a multiple of 17? Think. Yes, you are right. I cannot get every term as a multiple of 17. I'll get one term left which doesn't consist 17, or 17 power 0 will be there. That means the value is 1. So only one term will be left which doesn't have the value or the value 17. That means if I express this whole thing as 102 c naught plus 102 c1 like that and so on, I'll end up with, if this is taken as a, the last term will be 102 c 102 power into 17 power 102 minus 102 0 into 8 power 102. That means these whole terms will be divided by 17 easily, but not the last term. Why? Because it doesn't consist 17, but it consists of 8 power 102 by 17. Oh, it's very easy. It's already the same thing we have discussed in the previous method. Right? So now I have to solve only 8 power 102 or 2 power 306 divided by 17. Right? So again, can I take this 2 power 306 something sum of 17? It's not possible, right? 2 cannot be expressed as sum of 17, but I can. How? Can I take 2 power 4 from this 306? 306 is a multiple of 4? Not. But if I express that as this 306 as 304 plus 2, Okay, that means 2 power, let me rub this and clearly say this one. I'll express this 2 power 306 as 2 power 304 into 2 square. Okay, now this 306 is written as 304 into 2 square. Yes, it's possible, and this whole thing has to be divided by 17 again, and this can be equated to this as a 4 multiple. If 304 is a 4 multiple, can I write that as 2 power 4 into, what is the multiple here? 3 7s 28 and 24, 76 into 2 square. Can I write that? Why am I writing all these things? You will understand. 2 power 4 power 76. So what this is? This is 16. But I will not write 16 as 16. Why? I will write it as 17 minus 1. Can I write 16 as 17 minus 1? Yes, exactly. 17 minus 1 power 76 into 2 square divided by 17. Again, binomial expansion theorem, but in terms of a minus b. So if you see the expansion of a minus b power n, you will come to understand this is a very easy expansion. Yeah, I am taking time now to explain all these things, but if you apply all these things in your general general things, solving things, you will understand how easy this is. So it's nothing but a minus b whole power n can be easily expressed as nc naught into a power n, the same thing as a plus b power whole power n, but here the thing changes, that is b power 0, but what is the coefficient of b here? It's minus 1. That means the minus 1 will get the power of b. Okay, so you can explain this whole things. Here the last term, what would be the last term? Why I am concerned about the last term? Because it's in the last term itself I will not get 17. So I am concerned with the last term only. So what is the last term? The last term is 76. C 76. What is a there? 17, which has a power 0, because 76 minus 76 it's 0. So it's 1 only. Minus, so it's minus 1. So I'm taking it as minus 1 whole power 76. What will be this value? Exactly, the value will be 1 only, because minus 1 has having an even term here. Okay, so if there is an even term, minus 1 power even term, it will be always a positive. So I'll end up with 1 by 70. That means the remainder is 1 for only this part. This 2 power 4 power 76 or 2 power 304, I'll have the value as 1. But I left 2 square, right? Don't forget about this. That has to be multiplied now. So 1 into 4, the answer will be 4. Okay, the remainder is 4. Okay, I hope you understood this method of binomial expansion theorem. Again, this problem may not be solved with only 1 or 2 methods. It can be solved in many methods, like Little Fermat's theorem and Euler's theorem. So while solving this problem, we can solve it in also Little Fermat's theorem method. So what is that method? Let us see. So in Little Fermat's theorem, it says that if a number is existing like this, that means here p is a prime number and a should not have any factors with this prime number. That means they two should be co-primes. For example, in this case, 25 divided by 17. 25 and 17. 17 is a prime number. 25 and 17 are co-primes, obviously. So 17 minus 1, that is 16. Okay. So when I divide this 25 power 17 minus 1, that means the prime number which it has to be divided with, then I'll get a remainder as 1. So this is a theorem said by Little Fermat's theorem. So that means whenever I multiply this 25 power 16, I mean, in how many ways I can multiply this? Okay, I can multiply 25 power 16 to this again. So we already remember that when I divide this whole thing by 17, it's nothing but this remainder into this remainder, isn't it? That means 1 into 1, again it will be 1. So I have to express this 102, 25 power 102 as 25 power 16 power something. Okay, but can I do that? 16 multiple. In 16 multiples, will 102 come in that? No. So what is a better method then? 25 power 16 power 6 is 96. So how much is remaining? It's 25 power 6, right? So 25 power 6 has to be seen now. Okay, this 25 power 96 will always give me the remainder one from Little Fermat's theorem. So I have to solve only this one. So 25 power 6 divided by 17 will be a problem from this big problem. You can express this in again binomial theorem, or a last what you can use, the reminders theorem. Okay, 8 power 6, it can be used as 8 power 6, or 2 cube into 6, what is that, 2 power 18, and 2 power 18 can be written again as 2 power 4 into 2, 2 power 4 of 4. I mean, let's not make it in air. So this can be written as 8 power 6 by 17. It's equal to 8 power 6 by 17. 8 power 6 can be written as 2 power 18 by 17. But can I write 2 in terms of 17? Yes, exactly. But only when I can express 2 power 18 as 2 power 16 into 2. Now this 2 power 16 can again written as, but wait, can I express Little Fermat's theorem here? Exactly. 2 and 7 are co-prints. 2 power 17 minus 1, it will give the remainder 1. No need to express that again. So 1 into 4, answer is 4. So do we get the same answer? Yes, exactly. So this is Little Fermat's theorem, guys. So what is that theorem says? Whenever a number is into exponent of a prime number minus 1, that is one number less than a prime number, and that number is dividing this number, then the remainder will be 1. So you have to express, I mean, there is no way that the problem is going to ask directly. That means they never ask you, for example, 2 is there and it has to be divided by 19, and it 2 power 18 is your question. No, it cannot be. So they will express this number in terms of like this 25 power 102 or something like that. Let us say 2 power some 1024. Now we already know that 2 power 18, only 2 power 18 gives me the remainder 1, or the multiples of 18. So you have to check 18 multiples in the exponent. So up till that you will get remainder as 1 when it is divided by 19, a prime number. Like that I will see, I will check for the remaining things. I will check for the numbers which are not multiples of 18. So that will be left here. So 2 power some x, then I will solve this with only 90. Okay, so in this way we will find the reminders. Okay, even the easiness depends on your practice. Not exactly I can say which theorem is easy. For some people binomial expansion theorem will be easy, or some people multiplication of reminders will be easier. For some people Little Fermat theorem will be easy. Coming to the next theorem, it's called Euler's theorem. The same question has to be solved using Euler's theorem. So what is Euler's theorem? Euler's theorem states that whenever a number has an exponent, let's call that as a totient. When it is divided by a number, let it not be any prime number, any number, it can be any normal number also, composite number also. When a number, exponent number is divided by a composite number or even prime number, it has to be expressed like this. It will leave remainder of 1 only when, okay, this whole number will remain when divided by n will leave the remainder 1 only when if this phi of n or totient, they call it as totient, let's say the exponent, okay, this exponent is nothing but this n into 1 minus a into 1 minus 1 by b, and so on. What is this a and b? Don't worry, now I'm going to say that those a and b are nothing but prime factorized form of this n. That means if this n is expressed as a multiples of a, b, c of any powers x, y, z, then phi of n will become n of 1 minus the first prime factor into 1 minus 1 by second prime factor, and yes, I missed this 1 minus 1 by c. Okay, what it gives, what exactly it gives, maybe you don't understand all these things. Let's apply that to a normal problem. Okay, let's say a number has to be divided with not 46, but let us say 36. Okay, let the number be some x. Okay, it will leave remainder or 1 only when this exponent has to be, what it has to be, let's see. Okay, or phi of this quotient, okay, should be equal to 36. First, let's express 36 in terms of prime factorization. 36 can be expressed as 4 9 36, that means 2 square into 3 square. Okay, the prime factors are 2 and 3. Now 36 minus, what is the first prime factor? 2. So 1 minus 1 by 2 into 1 minus 1 by 3. Now what is this? This is 1 by 2 and this 2 by 3. So if I cancel these things and 3 12s, this phi of n is power is 12. That means there are 12 co-prime numbers less than 36 are existing below 36. Okay, they are saying that they are co-primes, not just primes, they are co-primes. 12 co-primes are existing less than 36. That means if this x power 12 is there and it has divided with 36, and if the both are co-primes, it will express as, it will leave the remainder as 1. Okay, can we apply that here? 25 power 102 divided by 17, but it will leave remainder 1 only when this 25 power has to be totient quotient. What is the totient? 17 minus the prime factor of 17 is nothing but the 17 only, because it is a prime number itself. Okay, so it is 17 into, so the answer is 16. That means there are 16 co-prime numbers existing below 17. Yeah, because 17 is a prime number, every number below 17 is a co-prime. So there are 16 co-primes. That means 25 power 16 when divided with 17 will leave remainder 1. Don't confuse this with your previous theorem, that is Fermat's little theorem. Even though they both look same, but it is different. Okay, Fermat's little theorem we can only apply only when the remainder, I mean the divisor is a prime number. Here we can express even, I mean this number is a composite number also. The divisor is a composite number. So 25 power 16 will give remainder 1 when it is divided by 17, because this is an Euler's quotient coefficient. Okay, so again this problem can be easily solved just by, we have to see how many 25 power 16s are there in this 25 power 102. So we express that and again we will end up the answer as 4. So I hope this remainder theorem class solved some of your doubts, like Euler's theorem, little Fermat's theorem, binomial expansion theorem and everything. If you still have any doubts in this remainder theorem, you can always comment on the comment section. We will come up with a new video. Thank you guys.